Now we've got Shagan, who's going to tell us about Ty. I think if people are in the Python community, you've probably heard of this really cool typing...
Type checker?
Type checker, yeah. But I'll let you explain it all. So
thank you.
Take it away. So thank you.
Welcome. Hello, everyone. My name is Shaigan, and I want to talk about type checking Python in Rust. This is about a project called TY. It is a type checker for Python from Astral, the same people behind Rough and UV. Both are very popular projects in the Python ecosystem. It is available as a CLI tool. It connects to your editor via language server protocol, so you can use it in VS Code and Vim. And it's also available on play.ty.dev, where you can run it on the browser. It focuses on speed and rich diagnostics. As you can see, the benchmark is pretty fast. That's for running TY on the CLI for type checking your whole project. But TY is also pretty fast when you run it on the editor, because when you run it on the editor, the type checker needs to constantly type check what you are typing and what your project has to give you accurate auto-completion and diagnostics. And for that one, TY made a couple of decisions that really help to achieve that speed, which I'm going to be talking about in the next slide. So this is going to be more technical talk. And yeah, I'm a contributor to TY. I'm going to be talking about some of the interesting aspects of the internals. So before looking into it, I'm just going to give you a very small example of what a type checker does for you. So this is a Python piece of code that I have. I have a function. It should be taking integer as an input, and then I'm calling it with a string. Obviously, if you run this, you would get an error in runtime. With a type checker, it would tell you that, hey, you're passing a string literal here instead of an integer, so it's going to obviously error on the runtime. But it's also inspired by the Rust compiler, which you might be familiar with, that it gives you more information about what other things can be helpful to fix this type error for you. So here, for example, we do show the function signature and the parameter that is declared, so you can get some help from the type checker to fix the problem. Now, let's look into how a type checker would work in a very simple way, just an overview. You might have a type checker that has more components than this, but this is the standard things that you would have in a type checker. So the type checker consists of a couple of passes that run over the source code, and each one produce some data structures that the next pass can use to do more stuff on the source code. And then finally, we have a lot of information, and then we can do the type inference, because we know about all the variables, all the functions, and everything, and we can do the type checking. So what does the parser does? Well, it takes your source code as text, and then it will transform it into a set of structs that we have. So it's a big statement enum with a lot of structs in it. And because every Python program is just a set of statements, you can convert any line of code that you have into a statement, or a couple of lines of code into one statement. And then in the later parts of the program, you can work with those statements instead. So we can do matches on them and cover all the edge cases. And you can see here I have I'm defining x with annotation int and assigning 1 to it, and I capture all that information into this struct. And here the value is an expression, annotation is an expression, the target is just a name here. Then we have the semantic analyzer, which goes over the AST that parser produced for us, so goes over all of the structures. And then we would try to derive more information from that. Things like, what are the definitions in my program? Functions, classes, scopes, all these things. What are the variables defined? So I have all of this information, and then later in the type inference, when you're assigning another variable to another variable, then the type checker can ask the semantic index, where is this variable defined? And I have all these definitions indexed in the semantic index, so I can look it up and do the inference. Then finally, we have the type inference, and it just goes over all the statements and expressions I have in the program and infer a type for them. So here I had int. It was an annotation. It's an expression, so we infer the type of it as class literal int. It is referring to the int inside Python. Then I have 1 and x, both are the same type because 1 was assigned to x. Now let's look at the semantic index more close with some examples of stuff that it records for us. Here I have a class and a function inside of it, so a method, and then these two create two scopes. I have classes scope, and then I have the function scope. We need to record these scopes, so later when you, for example, are looking up variables in the method foo, then you can know what are the parent scopes, so you can walk up the scopes and see what are all the variables that are visible to us there. And we do this by recording every scope into a vector. We just put scopes in the vector. Every scope gets an ID, so scopes can refer to each other via an ID. That's where the file scope ID comes in, and scopes inside themselves have their parent attribute where it just points to another scope with that ID. This is a pattern that you would see in TY a lot with having IDs that refer to stuff, so you can have the IDs inside different structs to point to each other, and then you would look up the vector with that ID to get the actual information. Another example of stuff we record are definitions. So here I have a function is defined, a parameter is defined for that function, and all of these are recorded in the hash map with the node key with all the definitions. A thing can have multiple definitions in Python. You can just overwrite the stuff, so you need to have all the definitions for that. And we also record the constraints. So constraints are two kinds. You have a narrowing constraint, like the if statement I have over there. I'm saying x is either type of integer or none, and then I'm checking if x is not none. So then this would narrow the type of x in that if branch for me, and it does that by recording all the constraints within the scopes, so I can know what is the type of x inside that if statement, and then it would be integer. Then I have reachability constraints, and these would be things like you have an if statement that would say if Python version is bigger than this 3.11, for example, define this variable, and then the type checker would record that reachability constraints, and then if you type check a project with a smaller Python version, then it would know that that part of code is not reachable and that variable should not be defined, and you get an error if you use it. Then let's look at the type inference with more examples. So here I have, again, a small piece of code, and the type inference is a set of calls that recursively call each other until all the expressions are inferred. So in this example, if you focus on the second result, a plus 3, we would call infer expression. That is just a big if statement, and then it would call the appropriate function that should be infer binary expression here, because that's a binary expression. And then that again needs to call infer expression, so it's recursively calling itself with a and 3 to get the type for those things. And then finally, based on the type of those things, it knows that what happens when you add those things up and gives us the final type. And this is the big if statement I talked about. So it's a match statement on the expression enum, and then we have cases for all the different expressions that you can have for in a Python program. Here, just one is a number literal, so it matches the case, and we infer the type for it. For the result a plus 3, it's a bit more complicated. I need to call infer expression again on a and then on 3, and then it would resolve where a was defined in the previous line, and it was assigned 1, so the type of it would be literal 1. And then finally, with the two things I have, again, I have another big match case where it has all the result for what happens when you apply add on two integer literals, and it has different cases for all the other types that you would have. So this was about the usual type checking stuff. One of the things that TY does that makes it fast in the editors is incremental type checking. This is about only type checking what you need and when you need it. So imagine this program. I have a main.py and a lib.py. And main.py is only importing a part of lib.py, and it's not depending on all of it. So when I type check main.py in my editor, when I open main.py in my editor, TY only infers the type of the types in lib.py that I actually need. And in this case, it would be the square function, and it would just skip over the square root function. And also, when you as you work with more files and more files, it will type check those. And it also caches this stuff for me. So if I don't change the lib.py at all, because it's a library, and I just focus on main, it would reuse the cache from the type inference. So you never need to do the compute again and again. And the way it does that is through a library called Salsa. It is, if you're familiar with Rust Analyzer, it also uses this. And Salsa provides us a couple of components that we can build our compilers, type checkers in this way with the incremental compute model. And here's an example of one of the things that Salsa provides. So this is what we call a Salsa query because of that macro at the beginning. And this macro is telling Salsa to track this function. And let's see what it does it track. So I pass the function a database. The database is used to track things like what this function does and the memoization of the function. It is a central database that Salsa just stores everything inside of it. So every query gets that database argument. And then I'm passing also a definition to it. So I want to infer the types for this definition. And inside a function, I am calling two other queries, again, parse module and semantic index. And Salsa records that this query depends on these two other queries. So if the results of these other queries change, it means that this query is also invalidated, so I need to recompute this. Otherwise, if the input is the same, these queries will stay the same, I can reuse the compute. So you would have a graph that looks like this kind of, so input and the call and what it calls, and then as long as those things are staying the same, then I don't need to recompute the value and I can just use the cache. This is the database that you saw in the previous files. It's just a Salsa DB macro, and Salsa does all the stuff for us. Salsa also provides a couple of other macros for our structs. So we have the Salsa input macro. This one tells Salsa that this is an input to our program, and you can think of, for example, the source code as an input to our program. And we can mutate the input because that's what the user changes. The other things that we have are intermediate values that we are computing via our query functions. And the input is the thing that users mutate. Then we have the intern structs. Interning is a technique to, if you have something repeatedly happening in your program, you can just store one of that thing once and then refer to that thing. For example, if you have a function name, and then if you encounter that function name over and over again, once it's defined, once it's called, and so on, you can store it once and then get back an ID from Salsa, and with that ID, you can refer to it. So you just allocate the memory once, do the syscall once, and then just have the ID. And then if you intern something over and over again, Salsa just gives you back the same ID. Also here, if you intern the function type, if we have a lot of functions with the same type, it's just going to be one object in our database, and the rest are going to be using that. And then we have the queries that we just looked at. So it takes the database, something that implements the database crate with the DB lifetime. So as a result of this, all of our structs would be copied. We can pass the stuff around. You don't have the problems that people usually face in Rust projects. You can move stuff around. You don't need to clone. You don't need to worry about it. It's just an ID. Everything, all the field values, all the stuff are stored in the Salsa database. You need to look them up in the database when you actually use them. But if you just want to pass in stuff, it's an ID. And most of our structs will get the DB lifetime. This will help us to, for example, if you want to pass references around or return references, everything has this DB lifetime. So you also don't need to really worry about what should be the lifetime because it's all DB lifetimes. And then it also prevents some things like, for example, mutating something in the middle of when you are using a cache value and stops you from mutating the input, for example, at that point. In order to take advantage of these functionalities that Salsa provides, we need to think about the problem a bit differently. So if I just infer all of the Python program all at once, or all of the file all at once, if something in the file changes, then I need to redo that again. So the caching is not as good as it can be. One technique here that TY does is you split the inference into multiple regions, so to scopes and definitions, and then if the file changes, some of that inference region can survive because if you touch something that is not affecting other scopes, then other scopes can still be in the cache and can reuse the caching. So same with the inference. Also, we have like a smaller query. So for example, here we can depend on the place table instead of depending on the whole semantic index if something is only using that. Or we only infer the definition types instead of inferring the whole program all at once with one giant query. Well, Salsa does a lot of nice things, but it's not done yet. Here's another big problem that you would face in type checking, and that is cycles. Cycles happen usually when you have a thing that refers to itself, and although it might seem, I don't know, confusing, but this can actually run as a Python program because someone can make an object of D and then assign X to it outside of this class, and then create another object and just call dCopy with the other object that they assigned the X to. And this can work, but from the perspective of a type checker, if we put ourselves into the shoe, it would be exactly like I'm trying to find out what is the type of self.x. To do that, I need to know what is the type of other.x. The type of other is D. So I need to go to the class D and find the attribute X, so I know what is the type of self.x. And that was exactly what I was doing. And those infer expression calls keep calling each other repeatedly until you crash, or you never actually quit. So this kind of loop happens. And Salsa has a solution for this. It is called fixed point iterations. With fixed point iterations, you would have, so let's think about a problem again. We have one function calling another function and then finally calling itself again. If we have some kind of if statement at a function, so it knows when it calls itself again, then it can stop that infinite loop from happening. But then we need to know what should we return at that point. We are calling ourselves again, and you can set the cycle fn and cycle initial attributes in the Salsa tracked macro, and it would exactly do those things for you. So cycle initial would tell Salsa what type should I use when I'm calling myself again and I have no way out, and it would return that type. So you can have all the functions that recursively call each other do their compute and then finally resolve, and then you get back to the first function that called itself. And then you would have two things. I assumed a value, and I also computed a value. Are these two things the same? If they are the same, I assumed something and I ended up with the same thing. So if I do that again, it will also be the same. But sometimes you might assume type never, which is the bottom type in Python. It is representing as this thing never happens. And if I assume something like type never, and then I do my computation, and then I end up with type unknown, well, this is not valid. So I can do this cycle again. I would iterate again. I now have type unknown, and I can say, okay, assume that I have type unknown, and do the compute all over again. And if I ended up with the unknown type again, then it means that if I just do that over and over, it's just going to be the same result. So it's at least stable. It converged the cycle. Otherwise, if it never converges, you might have something that just toggles between two values or things like that. Then the cycle has two ways. You can either iterate until some time that you would panic, or you can also fall back into an unknown value and just say, I couldn't solve the value for this. And yeah, this is really helpful because with all those recursive calls that you have, manually instrumenting your code would be a big hassle. But Salsa does this for you with this solution. Then we have the testing framework in TY. It is built in-house. It is a very nice thing. So all the tests, a huge chunk of the test suite is written in Markdown. And we have big Markdown files with Python code snippets inside of them. And then we explain, for example, this test case is testing this behavior. And then inside the Python code, there is a magic function like that reveal type. And you would write your own Python program. And you can use the reveal type to assert that the type of that thing is what you want, so in the comment. So it's a valid Python program, and it's also a test case. And here I have, for example, revealed int. It is not an int. It is literal 1. TY tries to be very specific with the types when it knows about it. So it knows that you assigned 1. It is definitely literal 1. And when you run cargo test, you would get a pointer to that annotations MD file. So that's your test case, and then the exact line that the problem happened, and then it will say, hey, it reveals literal 1, not integer. And whenever you submit PRs to TY, there's a huge sort of test suite that runs. Well, we have those MD tests, the same Markdown tests I just showed you running. Then there's conformant tests in Python. That's the thing that Python Typing Council works on, and they have sets of rules of what type checker should show for different annotations. And then it also runs on a lot of open source projects to know, what is the impact of your change on these projects? How many more diagnostics are you showing? What are your memory and timing metrics changing? And this is an example of one of those reports that you have, and then you can go to the projects and see, for example, what were the new diagnostics that you added. And which is very helpful for if you don't really know what's the right answer for some decision, you can just try it out and see what happens on the open source projects, because people write Python in a lot of different ways. Oh, that's it. Here's my blog. There's more Thai blog posts.